All right, we're ready to get started. So we're going to do a couple of activities tonight, both physical activities and also packet tracer activities. We're going to do the packet tracer first so you can understand kind of logical what's going to happen. And then we're going to do the physical just to make sure you also get that, okay? All right. So open up packet tracer. So once you've got packet tracer open, then I'm going to show you what I want you to do first, and then we'll move on from there. So first off, there are many different topologies you can have on a data link layer. Topology represents the physical but also the logical structure that you have on a network. So there are many different structures you can have. One of the most common is a bus topology or a point-to-point topology. Older Ethernet networks were bus topology. You had a single cable strand that all the machines connected to. That was called a shared media network. So we're going to talk about shared media networks here for just a second. Now, did I have you do the hub thing last week? You all plugged into a hub?
Yeah.
And we tried to get it to work? We did get it to work? Okay. So you did the hub thing, so you saw that actually happen, which is good. So let's go ahead and just play around with a couple of concepts just to make sure you've got it right. And then we'll make it a little bit more complex as we go, and then we'll just see how far we get. Okay? So first, you're going to put two machines out here. So put two machines. And step one is we want to connect these machines together. So in order to connect, now this is concept number one. It's kind of important about Ethernet topology. Your network card has a transmit and a receive. There are actually, on standard Ethernet, it uses, the cable that you plug into is an 8-wire cable. 4 pairs, 8 wires. On traditional Ethernet, it uses 2 pairs. 1 pair for transmit, 1 pair for receive. Make sense? So if you have 2 network cards, transmit and receive, and you plug a cable between them, right? So if my cable always communicates on 1 pair transmit and 1 pair receive, right? So if I plug a cable from here to here to 2 network cards, what's going to happen? So if I were to plug PC1 or PC0 to PC1, what would happen? Well, effectively, transmit would be going to transmit and receive would be going to receive. So the question to you is, will that work? Yeah, because it would collide, right? Very good, so that would not work. So a standard pass-through cable or patch cord will not work in this scenario. So in this scenario, what would we have to do? We'd have to actually have a physical cable that crosses transmit to receive and receive to transmit, right? Now, this would be actually a full duplex communication. CSMA-CD would not be required. Why?
Because it can transmit and receive at the same time.
Yeah, there's no potential for conflict. This is actually 100 meg. If this was a Cat 6 cable or Cat 5 cable on a 100 meg card, you could have In your case, you have a 1,000 meg card. So if we have a Cat6 cable between your two machines, this would be 1,000 megabits per second transmit and 1,000 megabits per second receive. So your effective bandwidth would be 2 gigs per second, right? Because you can transmit and receive simultaneously. You follow me on this? Now, let's go ahead and experiment with that scenario to try to get it to work. So what I want you to do, and I'm going to try to give you no instruction on this for the first few minutes. So I'm trying to get you to the point by the end of this class where you can take a requirement and implement it both on a diagram like this and also in real life. So we're going to be doing a couple of these exercises. Like I said, we started last week. We're going to do another one this week. We're going to do another one. So we're going to do several of these exercises to get you slowly up to the point where you can build a network, a small network on your own without assistance. So tonight we're going to get further into that. Last week I let you play around a little bit, and most of you did okay. You got the hub working. So we're going to continue the same process. So go ahead and connect these two machines together in Packet Tracer. Set these guys up with an IP address in a network. You might want to use a private IP address, 192.168.1 dot something, and set them up to where they can ping each other. So and prove that they can ping each other. So do that right now. You should be able to do that pretty quickly. And I'll give you about 10 minutes to try to figure it out. And if you can't, I'll walk you through it. All right, let's talk about how to do this. So take a look up here. So you're going to click on the lightning bolt, and you're going to choose the crossover cable. You're going to connect from the Ethernet to the Ethernet, right? You got that, hopefully. Then you got to give them, so that gives them a physical layer, and they're both on Ethernet, point-to-point, bus topology, Ethernet. Now you're going to click on one, and now you just simply got to go to IP configuration and give them an IP. So if you were to do like 1.1 with a subnet mask on one, and then you were to go to the other one and give them like 1.2 on the other one, they should be able to talk. You can prove that by opening up a command prompt and pinging the other machine. I had a brain meltdown there for a second. I just want to pause for a minute. All right, so I'm able to ping, so it's good, right? Now, another thing you might want to do is click Alt-D to clear out your ARP cache. Alt-D clears out your ARP cache. Now, another thing you might want to do is go ahead and click on the simulator, this little guy right here. Hold on. I should have dragged this guy more keyboard. So simulator. Now, what I'm going to do is I'm going to, while I'm running simulation, I'm going to go ahead and click on this guy, run the command prompt. This time I'm going to type that ping again, and watch what happens in the simulation. Notice that it first sends out an ARP. Do you recognize why it had to send out the ARP?
To find out the message.
What's that?
To find out the other computer's message.
Yeah, so hopefully you understand, you're starting to understand. Trying to go through this slow enough so you can get it. But notice that these machines have their IP addresses. So this guy knew this machine's IP and he typed it in. But he does not have the MAC in it. So what did he have to do? ARP for the MAC. So the ARP is a broadcast, right? That ARP is a broadcast. It's going to go out, and it's going to find out what this guy's MAC is. So watch what happens. So capture forward, there goes the ARP, right? And the ARP is basically asking, hey, I don't know your MAC, I need to know your MAC, right? So here comes the ARP reply. Now the ARP reply is not a broadcast, right? Because I knew what the source MAC was already. Now what can go out? What is able to go out now? The ICMP is able to go out directed to the IP, and now guess what I have? I have the destination MAC. Do you see that? So now here comes my ICMP. So if I look at my, here pretty soon will come the reply, right? And here's my first reply. And the ping command just by default does this 4 times. So here's the second one, back, third one back, and fourth one back. See how that works? All right, now, I want you to do this in real life. So, you remember how to, log on as your machine as the network account, right? So, it's name of machine / network, and the password is brute force. So I want you to log off your machines. You can say to your packages here, log off your machines, log on as you, and I want you to connect your two machines together and connect two machines together and see if you can get the same thing to happen. So you two can work together here, you two right here can work together, and you two can work together. Now you don't have to run a cable. You don't have to run a cable all the way from there to there. You can run a cable into the floor, and then up here in the patch panel, you can have a crossover cable connect your two ports together. You see that? So you can do a standard patch cord from your computer to the floor, and then up here you can do crossover to crossover. You can do a crossover up here, right? So what I'll do, somebody left their cable from last week. Bad. All right, so here's your standard patch cord you can use. Remember, leave the blue cable alone. And I will get you some crossover cables. How many do I need? 1, 2, 3. So here's one crossover cable. And I'll give that to you two. This is your guys' crossover cable. Last week, somebody found like 3 crossover cables. Now they're looking in the money to find them. But lock it and draw, you guys found them just automatically. Like,
yeah, your computer's a little limited.
You got to click the how do I log on. Click on the how do I log on. That's how you get your machine clean. I just got to find the box and crossover.
Maybe there's I see some people are starting to spin.
No, it's hard. Well, I mean, it might be easier for you to load it. Were you here? It really doesn't make any difference. So you're going to use that and we can enter it.
Then you can use it as a custom. But we can't do this. So I don't know what things.
So the rest of the money on just has to be split. So it says time that money to compute, that's the money.
Yeah, and then you just type net and you have to just brute force what you're doing there.
I have these, I have a box of that and crossover cable.
Wait, and use like a regular one, just got it something?
We put it into this.
Yeah, so,
These are all straight to the trails. You're not making them. It's still okay, but it's that's just cable. Well, we have one crossover, so they're done testing. It's over there.
You're gonna upload and the table from the back of the computer. Sure, I guess you can see if you can go. Which means that it's basically that kind of I guess that was like
I don't understand the side.
well, it's something that I use, though, right?
Yeah.
192.168.237.1. These are about the local areas we're talking about. Okay. I think it's just the very first one. Oh, wait. Oh, I have 3. I don't know. How many are there?
It's not the same then.
Well, they might have. What is it?
The one?
Yeah.
172 and
Okay, so they're good then. I guess we can try those.
So you can try
One,
them all.
yeah, so you can, okay, I'll do that.
172, 22, 37, 127.
No. Okay, let's try it.
The next one?
Yeah.
The next one is 192.168, 29.1.
So this is your second one?
Yeah.
Okay, I'm just trying to do what area comes to?
Yeah.
192, 168, 29. Wait, wasn't that yours too? Or repeating myself?
It's number 3. Is it 227.1?
Yeah. I think it's the first one. But, yeah. 172. 133. Okay, you're not quite sure then.
Here's 3 more. Did I need 3 more? How many more did I need?
Well, ours might be broken, so.
What?
It might be broken, actually.
Yours is?
They wouldn't in place.
You don't need it.
It's not working.
Here's another one. All right.
Hey, no, do you want me to walk your office and then leave?
I'm going to do that. So I'll show you what was happening. Do my log on right now.
Is that it?
No.
Oh.
But, okay. Let me open the file. I rebooted the machine. So maybe, okay, it's working now. Okay.
One of these
But
guys.
everybody's complaining about it, like all the students.
Can you, like, tell me what the problem is, but if you encounter it, if you could, like, do a, clip it and send me, like, a,
Yeah, God, I took a screenshot within the machine rebooted and I lost the screenshot.
Okay.
I thought for sure I'd replicate it again. But basically what happens is there's a VBA exception error, and it won't let you even close Visio. And it won't let you double click or open anything, and it's happening even when Visio is installed locally.
What are you doing, though, in order, when you just open it, it does VBA exception error?
No, when you try to do something like double click on something to bring up another property box. Anything that requires another property box.
So if you have one property box open and then you try to open up another one?
No property. Anything that requires a property box.
Okay.
Anything that requires a VBA property box. That's what kills it.
All right.
I'm not exactly sure what causes it to occur. But
Does it do it just here, or students try to use apps out in the state.edu and have
Everybody's complaining.
All right.
In fact, I don't know why rebooting the machine, because this is running on RDS.
Yeah.
So I don't know why rebooting the machine, rebooting the local computer fixed the problem. But I'm not sure why. That's strange to me. I thought for sure since it was already running RDS, running this again, it'd be running a version of RDS, right?
Right.
So why would that fix it? It shouldn't fix it at all.
No.
So I don't know what the deal is.
I mean, as long as it's using, maybe if it's like not really, it's using a temporary local profile, because
Yeah, maybe that's it.
you know, and then when you log in, it actually uses the actual profile. And sometimes it has that problem where for some reason it doesn't want to load the profile. And
Oh, here. Okay, I think I got it. Okay. So, open clipboard failed. Let's see if I can screenshot that.
I thought you said it said VBA.
No, I think this is what starts the problem.
Okay.
Okay, I'm just going to save this so we have it.
All right.
Under the first local area connection, we click on, and then we click on the, and then
All right.
under
So,
we click on
so now it allowed the clipboard to work. Yeah. Okay. Here's the problem. See, I'm trying to double click. Not opening.
Whatever you right click.
Go to properties. Nothing.
Minimize this.
So then what we did is we
Now, what? Two things open. I open up Word.
Uh-huh.
See, I open up another Microsoft program.
Uh-huh.
So I'm thinking that may have something to do with it. Okay, but let me see if I can get the VBA exception there. How do I get the VBA exception there? Oh, when I try to close it. Yeah.
We cannot quit Visio because a program is handling an event from Visio, which it's not handling. Okay.
No.
If VBA is at a breakpoint, reset VBA and quit it. Send me that.
Yeah, I'm going to send you these two.
Yeah. So what is that open clipboard? What did you do to get that?
I highlighted some stuff and Control-C.
Okay. All right.
This was not something possible to explain in the picture.
No. I had to do it. Not true.
Yeah.
Okay.
And what's the guy that works here now? What's his name?
Justin?
He's in my class. He saw the error.
Oh,
He can duplicate the error too.
all right, cool. I'll talk to you about it.
He knows about the error too.
All right.
So what?
All right, send me that stuff and we'll, I'll try to recreate it. And I'll try to do
Okay, cool. Thanks.
And you're going to send that email out tonight?
Yeah, I'll send it right now.
No, the other email.
No, I need to spend a few moments crafting. I don't want to say anything that would hurt somebody's feelings.
Okay.
I need to reread it a couple of times. I don't want to step on anybody's toes.
All right.
So it'll probably go out tomorrow.
Okay. Thank you.
Did you guys get it to work?
Yeah, but we have to set our own IP address.
Yes, you need to set an IP, just like we did in the packet tracer. Yeah, we're doing exactly what we did in the packet tracer, but you got to be able to do it. I want you guys to be able to try to do it by yourself.
We do IP version 4, right?
Yes. Make sure you do it for the right network card.
You said local area connection, right? So if you pinged each other successfully,
If you pinged each other successfully, you're good to go. Now don't stay where you're at, because we're going to do it. The next exercise we're going to do is going to involve you changing your IP. So just might as well stay where you're at.
I'm just trying to.
You guys to work? You guys got to work? Everybody got to work. Sweet. All right. Okay, so let's go back. You've logged on as a different user, but you should be able to open up Packet Tracer. So see if you can do that. Make sure you can. Okay, so can you do that? Does it work? Okay, good. So last week we put a hub into our physical mix. So we're not going to actually do that physically now, but I want to show you the difference. So we've got, I'm going to get out of this mode. Okay. So here this is what we got now. So I'm going to go ahead and remove this little guy right here. So I want you to put, let's go ahead and grab 3 PCs and stick them out here like this. Now, I want you to go to hubs, find hubs, and I want you to put a generic hub in between here. Generic hub. And we're going to use a copper straight-through cable to connect to that hub. You can connect it to any port on that hub you want to. Now, everybody got this? Pretty easy. Now the hub, and now what you want to do is configure, program all three of your computers with a different IP. So do the 192.168.1.1, 1.2, 1.3. So go ahead and program all three at different IPs. Okay, everybody got it? So now, what I want you to see is what happens when one of these PCs ping one of the other PCs. So we're going to go to simulation mode, and we're going to open up PC 0, and we're going to do the same thing we did last time. We're going to type ping 192.168.1.2, or some number, right? One of the other machines. And now, same thing happens before. The PC does not have the MAC address for the machine. So what's going to happen? Now let's watch as so what kind of frame is this? What kind of Ethernet frame is this? This is a broadcast frame, right? Because it's an ARP, right? So click capture forward and watch what happens when it hits the hub. So it's going to go to the hub. So here this frame is at the hub, and it is a broadcast frame. So this is going to go to both machines. You see that? So this hub is a physical device. So when our broadcast frame went to here, right, it went to both machines. Now, which machine is going to look at that? Well, at a physical level, they're both going to look at it. At an Ethernet level, they're both going to look at it. At an IP level, only the one machine's going to look at it, the one with the matching IP, right? So that's what's going to happen. So let's go. Notice that they got a red X next to this one because it doesn't match the IP. So click capture forward. Now this guy sends the ARP reply. Now I want you to open up the ARP reply and look at this. Now it's got a destination and a source MAC. You see that? This is called a unicast frame. Before it was a broadcast frame. Why was it called a broadcast frame? What's that? That is not correct, but I know what you're saying, and you're somewhat true, but that's not why it was a broadcast frame. Why was it a broadcast frame? That was the same thing he said. That's the result of it being a broadcast frame. Because it was set to all Fs. The Ethernet was set to all Fs. It was set to all ones, right? Now, before you click capture forward, what do you think is going to happen? What's this hub going to do with it? What do you think is going to happen? Do you think it's going to send it to PC2 as well? Well, look what happens. It goes to both. Now, I want you to wonder out loud now, why did it go to both?
populate the ARC tables on both computers with the other one?
Well, it is going to populate the ARP table on both computers. That is a result of it, but that's not why.
Which computer has which IP, so it just sends to all of them.
No, that's not correct. It doesn't need to do that because it knows the directed MAC. So it knows the MAC to send to. But why did the hub send it to both ports? Why did it do that?
Because it doesn't know what port the IP is on.
Not the IP, what port the MAC is on. Now, here's the kicker here. This is the point of the lesson. A hub is not smart enough to make this decision, right? Because the hub works only at layer 1. The hub does not work at layer 2. So if the hub had the capability of working at layer 2, what would it have the ability to do? To look at the MAC and know what port it's on. The hub does not make those kind of decisions because it's dumb. Right? Does this make sense?
Yeah.
Another word for a hub is a multi-port repeater. It just repeats the electrical signal at all ports. That's all it does. It's just dumb. Right? Does this make sense to you? Okay, so that's what happened here with the hub. Now, what I want you to do, let's get out of simulation mode. Click on the X and let's delete that hub. Now let's go down to switches and let's put in a 2960 switch. Right? And this time, let's connect all these guys to the switch. Doesn't matter what port. Oh, by the way, I forgot to, damn it. Okay, you don't have to do this. Let me just do it real quick. I don't want you to have to do it again. Let me draw this over here. Okay, so we have a thing called there's two types of things we have. One's called a broadcast domain, and one is called a collision domain. This is one giant broadcast domain. And when we refer to a broadcast domain, we refer to, on an Ethernet level, all machines that can broadcast each other. So these machines can all broadcast each other. They are all on separate broadcast domains. Does that make sense? The switch, they're still on the same broadcast domain. So if I were to send a broadcast from this PC, would it go to all ports? It's a broadcast, it's going to go to all ports, right? If I send a broadcast to here, it's going to go to all ports. That is the same broadcast domain. You follow me? A collision domain means that unicast packets do not go to all ports. So in this case, if I send a unicast, does it go to all ports? We just confirmed on a hub, yes. So therefore, these are not only in the same broadcast domain, they're also in the same collision domain. Does this make sense? They can all collide with each other because they're all using the shared same media network. However, how many collision domains do I have here? I have 3. Because each one of these have their own transmit to receive, transmit to receive, transmit to receive. This is one collision domain. You see that? Because there's no possibility of transmit and receive colliding with each other. Right? With the hub, what comes in goes out, right? So there's a possibility of a collision. Here, each port can't have a collision. So therefore, there are 3 collision domains in this case. 1 for each port on that switch. Whereas in this case, we have 1 big collision domain. Which do you think is faster? kind of. All right? There's a point of diminishing returns, right? So with just one or two machines, the hub is probably going to be faster because there's nothing in between you and the other device. It's all physical. There's no intelligence going on. With the switch, there's a bit of processing that occurs at the switch, which is going to slow the communication down ever so slightly. However, when you start increasing the number of machines, which one gets faster? The switch, because now we're more efficient. You follow me? So this is why you got, one or two machine network, the hub is going to be faster. Thousands of machines switch much faster. Right? Okay, so now let's go over here to our switch, and let's look at the behavior in simulation mode. Okay? So I'm going to simulation mode. I'm going to open up this guy, and I'm going to clear out my ARC cache, ARC-D. And I'm going to ping that other IP again, right? So just as before, he's going to send out an ARC, right? You're all familiar with why he's sending out an ARC, right? Capture forward. ARC is, now what do you think is going to happen? What is this guy? He's a what kind of frame? He's a what? It's not a unicast frame, it's a broadcast frame. So what do you think is going to happen? It's going to go to all ports, right? So watch what happens. There it goes, right? Goes to all ports. Oh, excuse me, man. I think it sent out 2 ARCs for some reason. What? Strange. It sent for 1.1. Why did it send for 1.1? I asked for 1.2. Whatever. All right, so here comes the one we're really interested in, right? Asking for 1.2. I don't know why I did that. So here it comes. It goes to both ports, right? Because it's a broadcast. So only one's going to get it. Now, here comes the unicast back, right? This is a unicast, right? MAC to MAC. You know why it's a unicast, right? It's MAC to MAC. What do you think is going to happen? Is it going to go to one port, or is it going to go to both ports? What? Let's find out. It only goes to one port. Do you understand why? So the switch, you're right, the switch is intelligent, right? The switch is intelligent enough to know that that MAC address is on that port. You follow me? So let's click on the switch now. Go to command line interface. And I want you to run the command show MAC address table. And notice what's going on here. The command show MAC address -table is saying the MAC address is on this port. This MAC address is on this port. Notice whose MAC address it does not have yet. See, it has this guy's MAC and it has this guy's MAC. Now, why does it have those two guys as MACs? How did this switch learn those two MACs? What port they were on? Because it saw the arc coming across. Right? It saw the arc happen and it was like, that one goes there, that MAC's coming from that port, and that MAC's coming from that port. Has this machine talked yet? This machine has not talked yet, so therefore we don't have it in the MAC table yet. Now, if I were to try to suddenly send a directed frame to this machine, and the switch did not have its MAC address in, so if I send a unicast frame to this machine right now, and I did not have an entry in the MAC table for that MAC, what would happen, do you think? Would the switch just drop it, forget it? Or would it forward it? It would forward it to all ports, just like a hub would do. And this is, by the way, we call this a flood. So when the switch receives a destination MAC that it does not have in its table yet, it floods it on all ports. Does that make sense? So it floods it out the ports. So you now know what a flood is. Now, all right, that's good. So let's keep watching what happens here. In fact, I'm gonna go to real-time mode, then back to simulation mode. And this time I'm going to open up PC0 and I'm going to ping the other machine. And what I'm going to do is I'm going to bring up switch 0, and I'm going to show MAC address table. I still only have those two MACs in there, right? And I'm going to click capture forward. Here comes my art, right? Here comes my art. I'm going to run show MAC address table again. Nope, don't have the MAC yet, right? Capture forward. The broadcast goes out both ports, right? This is why this is called a broadcast domain. Oh, here it comes. All right, I just got the art. Do I have the MAC address table yet? No. Capture forward. Here comes the unicast reply. Guess what just happened? I just got the MAC address in the table. Now I know where all three machines are on what ports. From this point forward, whenever I get a unicast to that MAC, it's going to go straight to that port. So watch what happens. Here comes my ICMP, and my ICMP is a unicast, destination MAC, source MAC, right? Is PC1 going to know that PC0 and PC2 are cheating on him? Right? PC0, it was a joke. You guys aren't even laughing. All right, so PC0 and PC2 are talking, right? PC1 has no idea these guys are carrying on a conversation, right? PC1 does not have any clue this is going on, right? This is reducing, or this is increasing available bandwidth. PC1 has more perceived bandwidth because PC1 isn't, the network is available for PC1 to talk right now. It's not being hogged by PC0 and PC2's traffic. Do you understand switch mechanics? All right, so what I want you to do is get yourself into a switch. So I think you all have a switch, actually. Okay, so you two do not have a switch. So I want you two to get yourself into that switch. Switch number 14, and you'll make sure that it has power. Switch number 14 does not have power, right? So it'll require you to figure out how to plug it in. Okay, you two will use switch number 10 right here. So you need to get your two machines plugged into switch 10. Do not use crossover cables. Okay, you two will connect to, I don't want to switch 6. Yeah, you switch 15. Get yourself both plugged in switch 15. And you'll need to get the power on, right? It's not powered on right now. Well, the other way to do this is to go into the floor, out here, into the jack, out the jack, into the switch. So you can do it that way if you want to, or get long cables. Whichever way you want to do it.
I don't know. And then you would need
Just go from the back of your computer and switch.
So the way to both connect to the switch.
Yep. It'll take 180 seconds for the switch lights to turn green. Power.
Yeah, you plug in and like, I don't see the green lights. You know, well, your switch is on.
It happens the best.
What's wrong? You said, okay, you can help me out.
Happens to the best of us.
Oh, okay. Wait, do you think they can like me? I think we're wait. Fix the switch from the number, double click together. I didn't know that.
Having problems.
What's wrong?
It's not working.
Wait, is it supposed to be 3 computers?
And the thing's broken.
Do I use that cable?
Well, we're not. I'm just letting you know.
It's not working. Do you have link lights?
Yeah. It's not working when we try to ping each other. Using the IP addresses that we already put on.
What port are you plugged into on this right now?
Random one.
Try 2 ports right next to each other.
Okay.
Could be just that the switch has been configured wrong.
Do these have 3 computers?
What?
These have 3 computers on, right?
No, just 2. You can do 2 computers in a switch or 3.
Okay, so it's all mixed with each other.
Takes 180 seconds. I think it's more, well, maybe 90 seconds. There's a process called spanning tree. Each phase of spanning tree, I think, is 30 seconds. There's 3 or 4 phases. Still no work? That's just what you're looking at. The mode tells you different status indicators, but it doesn't change the behavior.
You always think it's a turn.
Well, it doesn't let somebody program the switch. But I don't know if somebody did that. There's a potentiality for the switch to be open. So there is a cost.
Yeah, no, I think you just said
Do you definitely have your FTs right?
Yeah, we already did them the first time.
Okay, try it again. What?
Yeah.
Alright, so I think your switch is going to be. Alright, so good. Did everybody get to work? Broken cable? Little plastic thing you broke? You guys get your switch work? Yeah, your switch work. Okay, so now plug into the switch. Supposedly you're more efficient now. So you now have the idea of programming the switch. Now, the other idea, though, is that we would like to be able to program that switch. So from a computer that's close to that switch, what you're going to do is you're going to connect a console cable to the switch. Let me show you how to do it. So in Packet Tracer, I would take a machine and I would grab a console cable and I would go for my RS-232 serial cable port on the back of that machine and I would plug into the console port on the switch. So I have this little blue cable now connecting to the switch. Now when you open up the switch, actually when you open up the PC, you can now open up a terminal, and when you open up a terminal, it's going to be 9600 8N1, and when you do that, you open up a terminal and you can connect to the switch. This allows you to program the switch. So you're going to do this. First off, you got to make sure that you have PuTTY on your computer. You do. I think you have putty. What?
Yeah.
Putty. Well, that's what it is. Putty. It looks like this. Putty. So here's what you're going to do. Go to the machine that is near your switch. Yeah. Log on to it as that network account. And then you should already have one of these in the back of that machine, but if you don't, there's one up here. This plugs into the switch's console port, and this goes into the 9-pin serial port at the back of your PC.
Where's the switch's console port?
On the back of the switch, it looks like one of these. So this goes to the PC, this goes to the switch. So, but I believe there should already be on the back of that machine. There's already probably a console port there. What? Yeah, I got to show you how to do putty. So when you've got that console cable in, you open up putty, and you're going to click on serial right here. See where it says serial? You're going to make sure it says COM1. You want it to be 9600 baud. And then click open. Then hit enter a couple times. So TTY is a teletype interface, or is what it tells, something like that. And I'm not sure what the packet. I think P stands for, I don't know. Actually, I don't know. I know TTY is a common term for remote telnet interface. So PuTTY, I don't know what the P is, probably for packets over TTY, or the U doesn't stand for anything. The P and the TTY do. They just thought it would be cute to call PuTTY. It's asking you for user access verification.
Yeah. And then it says password time expired.
Did it ask you for a username or just a password?
It just says user access verification.
type Cisco.
And I just looked at it a couple times and it said S1 from 0 is not good. Type Cisco.
You ever to get into it? What do you see? Router? I shouldn't say router, I should say switch. Are you sure you're plugged into the, make sure you're plugged into the console and the switch, not the router. Double check, because I think you're in the router. You guys get it? What's that? So is this guy's serial port plugged into the console and the switch? What? Cisco. Got it? Yes. So now here's show actors. There you go. Now you're seeing all those MAC addresses. Right. And you should see your machine. Under which you branch. There you go. So pick up your machine. You get you a switch. So now type show MAC address. Do the show MAC address table connect. Yeah, you want the 9-pin serial that connects to the console port and the switch. Static means that it's been hard coded or manually programmed. Dynamic means it's picked up. Dynamic change. Static that also. Did you get your MAC address table? Do you see it?
Yeah.
Do you see your machines, your Macs?
Yeah. Number 4 on the back and forth. So I wonder if those are the ones on the end that we were trying to put in there. Wait, how did it go?
Yep, I think so. Do you guys get it over there?
I'm not sure.
Did you get a reply, text back when you hit enter?
Yeah.
What does it say?
Switch from there.
So type show MAC address, just like we did on the.
Yeah.
Do you see your MAC addresses?
That's it.
You do? Good. All right. Now, the other thing that you need to know about these switches is just the concept. So when a switch gets a frame, it needs to make an intelligent decision as to where to forward it based on its bridge tables. What you're looking at, the show MAC address table is called the bridge table. It tells us what MAC is on what port. And you know what the consequence is if it doesn't have a MAC in there. It will flood it, right? So you got those concepts down. So hopefully you understand the idea of the switch. The other thing the switch can do is if a frame comes in and it's got something wrong with it. So let's say a frame comes in, there's a problem with that frame. Do you think it's going to forward it or discard it? It's going to get rid of it. Why forward bad frames? So on your switch, you know what one of your machines is on, like FA01 or whatever it is. Can you see what port your machine's on? Type show interface FA0/1 or 0/3 or whatever one of your machines is on. Slash not that one. Slash. Yeah, you're on one, so you slash it. Not that one. Slash. Okay, now. What I want you to see there you'll see a 5, you'll see a 700, you'll see so many packets input, right? And then you'll see a number of runs, a number of giants, a number of throttles, a number of input errors, a number of CRCs, a number of frames, a number of overruns, a number of ignored. You see all that? It tells you how many runs, grunts, giants, jatters, all these fun terms, right? So there's all sorts of fun little Ethernet terms you got to learn, right? So sometimes you'll have frames that are too big for Ethernet. So Ethernet has a max frame size. So sometimes you'll see frames that are too big. So in that case, the switch will discard it because they're too big. Those are called giants. You see that in it, right? Other times you'll see frames that are malformed, like Ethernet is not correct. So it'll drop those. The big one, though, you got to watch for is the one that's CRC. That means that the cyclic redundancy check, the frame check sequence, didn't map out. So it'll discard those. What's that?
I was just going to ask you what the CRC was, and I need to show you something.
Yeah, remember the end of the frame is a thing called CRC. And that's where we check to see the consistency of the frame. Now there's a couple of ways that your switch can do this. In a low latency environment where we cannot afford dropped frames at all, the switches, you'll have switches that are called store and forward switches. Which means the switch will receive the entire frame in its entirety, process the whole frame, check its CRC before it'll forward it. Now that environment, you get really good protected frames. You absolutely know the frame is right. But you got to wait for the switch to store and forward. Other types of switches, which these are called cut-through, which means they don't look at the entire frame. They just look at the first part and the end, right? That's it. They don't look at the content. They just look at the beginning and the end. Just enough to get it going on its way. They don't bother looking at it. That's called cut-through, right? So these switches will not catch all errors because they're cut-through, but they'll catch the majority of the errors, right? Make sense? So cut-through is pretty common. They're lower cost switches. Store and forward tend to be more expensive. All right, so now you've got some basic ideas there on switch topology. All right, any questions about that so far? All right, let's introduce some more complexity. So get back on a machine where you have packet tracer. So let's introduce a little bit more complexity in our switch ideas. So right now our machines can ping each other and everybody's happy, right? So right now these guys can ping it. So PC0 can ping PC1, no problem. Everybody's happy, right? Now open up the switch. So on the switch, we're just going to do this in the command line. We're just going to do this in the graphical interface. I don't need you to worry about the command line yet. But go to the VLAN database. See where it says VLAN database? I want you to say number 2 and call it test. And click add. Yeah, number 2, VLAN name test. Then I want you to find out what port PC1 is connected to. So my PC1 is connected to FA02. So I'm going to go to FA02, click in the white space, and then hover your mouse over the green dot. So I'm going to go to Fast Ethernet 02 here, and see where it says access? I'm going to make it VLAN 2 instead of VLAN 1. Do you follow that? Now I'm going to close the switch. Now I'm going to wait for a minute until my orange dot turns green. It takes about 90 to 100 seconds in there. I think it's actually 90 seconds. I don't remember. I have to remember the timing sequence on spanning tree to remember. I don't remember. All right, so now that it's there, now open up PC0 and try to ping. And you're going to request timeout. What? Well, click on simulation, then back on real time. Oh, that's your problem. Go back to real time. Now, go to PC0, click on command prompt, and delete your ARC cache, ARC-D. And now, go to simulation mode and ping the other machine. And watch your ARC broadcast. This is a broadcast, right? Where is it going to go? Negative. So I'm going to go to PC2. So now we know why. Right, PC0 could not ping PC1, right, when we made that VLAN change. PC0 could not ping PC1 when we made the VLAN change, right? So now when we send the ARC broadcast, before it would go to this machine, it would get the ARC broadcast. But what happened this time? The broadcast came to the switch, and the switch ported to this port. I ask of you, why did it only go out this port? No, it's a broadcast. It doesn't know the map. It's a broadcast. So why did it broadcast only this port and not this port now?
Same, because you send on that port, right?
We made it a member of a different VLAN. So so this is really important to understand. So we took the switch and we created another VLAN. What do you think the V stands for? Virtual LAN. So we now have two virtual LANs. So what do you think that created? We created another VLAN and we assigned PC1's port to that VLAN, right? That's what we did. So what did we create? What's that? A separate broadcast domain, right? Remember how we had the hub, we had a broadcast domain? And actually this switch is one broadcast domain, but three separate collision domains. We've now created two broadcast domains, VLAN 1 and VLAN 2. And PC1 is in that broadcast domain. It is not going to get broadcasts from VLAN 1. It's only seeing broadcasts for itself. So PC0 and PC1 are segmented by separate VLANs. Do you understand this concept? If you understand this concept, you're well on your way to getting network. This is another hardware, right? So we've created a logical partition that separates the two segments, creating two broadcast domains. So how could PC0 and PC1 talk to each other if we wanted them to? We could put them on the same VLAN, then they could talk. How else? If they're in separate broadcast domains, what would need to stand in between their two broadcast domains? A router. So if we had a routing device that stood in between PC0 and PC1, and the routing device could forward traffic from PC0 to PC1, then they could talk. So the router is what is required to have two broadcast domains talk to each other. Right? Well, we don't need to, we're not going to go down that road right now. But you understand it, at least. You understand what creating a VLAN on the switch did. It created a separate broadcast domain. Okay, any thoughts about that? Now, the other thing that you need to consider is this. We could add another switch down here. So basically, yeah, go ahead.
How many VLANs can one switch be?
Well, that's a function of how big and powerful the switch is. I think these switches can support 1,000, roughly. Actually, I think they can support 4,096. What? It's a derivative of the power of 2. All right, so we could have created another switch, and we could move PC1 right? This would produce the same effect that I just did, right? So I created a virtual LAN, and I also created a, right? However, check this out. Now I'm going to go back to real-time mode. All right. Now I've got these switches connected together. Now I'm going to go to PC0. Let's see what happens. I can ping. Huh? What? Actually, R-D. Right? And now I'm going to ping. Let's see what happens. What's going to happen? The broadcast can get forwarded to all ports. The broadcast can hit this switch and get forwarded to all ports. See that? Because I trunked these switches together, I connected these switches together. This guy is connected to VLAN 1 on this switch as well. You follow me? You understand how this is working now? So because he's on VLAN 1 as well, they're in the same broadcast domain. And you notice that the broadcast went to everybody, including the PCs in that broadcast domain. They trunked them together. Do you follow? Now, if I were to have had a PC, though, if I were to take a PC and add it up here and plug it into this switch right here, right? And I were to open up my PC0, and I'm going to do my ARP-D again, and I'll ping. Because that PC's in VLAN 2, it's not going to get the broadcast. It's in VLAN 2. It's in a different broadcast domain. But everybody in VLAN 1 did get it. Now I'm going to go to this guy, and I'm going to give him Now, what I'm going to do now is I'm going to take PC. I'm going to go to switch 1 here. What port did I connect this to? Do you remember? FA01. So I'm going to go back to real-time mode. I'm going to go to switch 1. I'm going to create a VLAN 2. Right? I'm going to go to fast Ethernet. What was it, 01 or 02? I don't remember. 01. I'm going to make that a member of VLAN 2. Right? So this guy is now a member of VLAN 2. So 192.168.1.2 is a member of VLAN 2. So I'm going to go to him, and I'm going to open up a command prompt. I'm going to go to simulation mode, and I'm going to type ping 192.168.1.10. Here goes my broadcast, right? My ARP. Who's it going to go to? It's going to go across the trunk. Uh-oh. Oh, spanning tree gets in the way. Damn it. Okay. We have to let spanning tree do its thing. Okay. Okay. hold on. I gotta kill spanning tree. I gotta take spanning tree out of here. No more spanning tree. Yeah. Spanning tree bad. All right. So let me go. Okay. Oh, it didn't cross the switch boundary. Yeah, hold on. I know it's wrong. Okay, check this out. This isn't an access VLAN. So I got to make this a trunk. That's the problem. So I'm going to make that a trunk, and I'm going to make this a trunk. Okay, now I got two trunk interfaces. So let's wait for the trunks to become available. Yeah, what's supposed to happen is Cisco auto configures ports as trunks, but I guess Packet Tracer's not doing that, so it's not doing the behavior that I'm used to. So I'm going to open up PC1. I'm going to do my arc-D here, just to make sure, and now I'm going to ping at 1.10. Now, oh, it works, but I wanted to see it happen in simulation mode. So I'm going to ping it now. There we go. Now let's watch what happens. Hits the switch, gets forwarded across the trunk, and now where's it going to go to? I made PC1's port a member of VLAN 2, so what's going to happen? It's going to VLAN 2. Do you see that? Because PC6 and PC1 are on ports, they're both in VLAN 2. Now I want you to visualize this in your mind right now. Every one of these machines are on the same layer 3 subnet. 192.168, 1 dot whatever, right? They're on the same layer 3 subnet. But they're on different layer 2 broadcast domains. You see that? They're on different network segments. So even though they're in the same IP, they can't talk to each other via Ethernet. These two machines can talk to each other via Ethernet because they're on the same broadcast domain. They're on the same segment. These guys can talk to each other because they're in VLAN 1, and these guys can talk to each other in VLAN 2. You follow me? And this trunk interface is allowing the VLAN traffic to pass through the trunk. Right? Let's let that sink in for a second. Any questions about that? So if I wanted to get if I wanted to get VLAN 1 and VLAN 2 to talk to each other, I would need to put in a router. But I could not have them both in the same layer 3 subnet in that case, because the router wouldn't know to forward it to the 1.0 on one side or the 1.0 on the other. I would have to make one of them 1.0 and the other one 2.0. One of them would be the 192.168.1 range, and one would be the 192.168.2 range. Then the router would know to forward to one side or the other, right? Because the router would be handling the broadcast. Got it? All right, so you've now connected your machines to a switch, and you've now actually done this. So I don't know if you could. If you haven't done it already, can you duplicate what I just did right now? Open up Packet Tracer and try to duplicate what I just did right now. Create 4 machines, 2 switches, and try to get the machines. In fact, try to get the machines to communicate 2 different VLANs.
connect one to the console, and reference stage.
What's that?
Should we connect one to the console and reference stage?
No console required.
Version 173, version 6.
Yes. It works with IP version 6. All right. So I've made some complexity that I'd like you to just get your mind around, right? Did you get that working? We just did? So here's some complexity. So just like we did before, I've got PC0 and PC1 in the same VLAN, VLAN 1. I have PC6 and PC2 in VLAN 2. So they should be able to ping each other, right? So let's go ahead and test that theory. So I'm going to open up PC0. And it's 1.1. So I'm going to ping 192.168.1.2. And I get a reply. So I'm going to go and do arc-d. Now I've made a slight change here. I want you to know what your broadcast domains are and what your collision domains are. So I've added 3 more PCs on a hub, and I plug that hub into the switch. So in VLAN 1, how many broadcast domains, what are my broadcast domains? Well, VLAN 1 has a broadcast domain. So theoretically, where's the broadcast going to go? Let's go ahead and test the theory. So I'm going to go to simulation mode. I'm going to open up PC1, and I'm going to ping 1.2. Let's watch where my broadcast goes. You following? So it goes to the switch, right? Where's it going to go? It's not going to cross the VLAN boundaries and go to VLAN 2, right? You know that. It's going to go out VLAN 1. So anybody that's in VLAN 1, it's going to go out, right? So let's find out where it goes. So it goes to the router. But it also goes to this hub, right? Because the hub is plugged into VLAN 1. What's the hub going to do with that? It's going to forward it to all ports. It's the broadcast, right? It's going to forward it to all ports. See, it goes to all ports. See that? And PC2 is going to reply because it's the machine we're talking to. Okay? However, if we go back to this, if we go back to PC6, and I'm going to have PC6 ping PC1 down here in VLAN 2. Right? Let's watch that arc. It's going to go to the switch. Now, where's the switch going to forward it to? The same broadcast domain, right? So it's going to go to the router. It's going to go to this switch across the trunk. Notice it did not go to the hub. Why didn't it go to the hub? What's that? Because it's in VLAN 1, which is a different broadcast domain. Very good. And it's going to go to PC1. Do you see that? PC1 is going to reply because it's for it. And there it goes. The directed packet goes back to PC6. You understanding? I want you to make sure you conceptualize broadcast domains.
Why did it go to the router both times?
Aha! Good question. So let's look at the switch. I configured the switch, the port that connects to this router, as a trunk. The router, I also configured the router SAS Ethernet 00 with 2 virtual interfaces. So it's got 2 virtual interfaces on the same physical interface, and those virtual interfaces have been set to 802.1q, which is a trunking protocol. So it has got a connection to VLAN 1 and VLAN 2. So the router has a connection to both VLANs. So it is in both broadcast domains.
Connect the routers connect the routers so we can forward it both to VLAN 1 and 2.
That's what this is doing. It is connected to both VLAN 1 and VLAN 2. I did that with sub-interfaces. I could also do with physical interfaces. So I could have physically plugged it into VLAN 1 and VLAN 2, but I did it logically, so I only had to require one cable, right? It doesn't make sense to take a router that's capable of virtual trunking to physically connect it. Now, if you turn your heads and look back at those machines back there, they have a stack of servers back there. Every one of those servers have network cards on them that are also capable of .1Q trunking. So I can take a server, plug it into my switch, and set it up with virtual interfaces with .1Q trunking, and have it also listen to each of those VLANs as well. In fact, I think Packet Tracer allows me to do that. Let me see. No such luck. No, I don't have a fancy thing, but I do have, check this out. I do have an IP phone. So here's my handy-dandy IP phone. And my IP phone is capable, oh, I got to boot it on. Oh, it needs a power adapter. Oh, please. All right, so my phone also has the ability to configure into VLANs. So what I'll do is I'll take, and I'll connect that, let's say, to port 24, and I'll go into this guy and I'll make its port 24 a trunk. So the IP phone is just as capable of connecting to VLANs as your router is, right? So same kind of concept. Okay, so now let's watch what happens. What if I wanted PC1 I want PC1 to ping PC0, right? So I'm going to simulate this. And I'm going to ping 192.168.1.1. Now I want you to see if you can make sense out of what's about ready to happen. So take a look and let's go through it slowly. All right, what's the first thing PC1 is going to do? I'm trying to ping somebody in a different network. So what am I going to do? PC1 is going to ART for what? Can you remember? What's it going to ART for? MAC address of whom? No, PC0 is in a different physical segment. It's going to ART for, let's see who you think, let's see. Here comes the ART. I'm asking for whose MAC. It's going to go out VLAN 2, wherever VLAN 2 is, right? Who's going to reply? Guess who replied? The router. So I ART for the router's MAC. Now why did I ART for the router MAC? What's that? Yeah, so when I send my ICMP packet out, I'm going to send it with the destination MAC of the router, but the destination IP of PC0. So watch what happens with the ICMP packet now. There it goes, right? Look, source IP, 192.168.2.2. Destination address is the router, right? So here comes the ICMP packet. Oops. What the heck just happened? Right? There it goes to the router. The router now gets, right, this incoming IP request. What's the router going to do now? The router wants to get this ICMP to PC0, right? So it's going to ARP for PC0's MAC. So here that goes. Switch 0 is going to forward that MAC to all machines in that broadcast domain. PC0 is going to get it and forward it back to the router. The router now has that in its MAC table. Meanwhile, the original ICMP echo request failed because it took too long. So if I go back over to my machine here, not yet, but I will. What is that? Oh, yeah, okay. Okay. Request timed out, right? My first ICMP echo request fails. So now here goes my second one. Is this one, I'm going to send out my ICMP echo request. It's going to go to the router directed unicast packet. Notice none of these machines see it. It's unicast. It's going to go to the router. The router is going to unicast it. Now, why is the router unicasting and not ARPing?
Because it already knows the MAC of PC0.
Because it knows the MAC of PC0. And the switch knows the PC0 is on that port. Right? Here comes my echo reply. Back to the router. Back out on VLAN 2, right? To the switch, to the PC, and yay, reply. Any concerns about that? And of course, right, this just rinses and repeats a couple more times. Well,
The second time it didn't have to wait for us.
the second time it didn't have to wait for ARP. Right? If it lasts longer than a certain number of milliseconds sensitivity-wise, ICMP fails. I don't remember what the sensitivity is. But by the time it waits for an ARP broadcast to go out, ARP reply, ICMP sensitivity is expired. But the second time, the router didn't have to ARP to get the MAC. It already knew the MAC because it was in the router's MAC table. The router has an ARP cache just like the machine has. Right? See, because now PC1 now has the router in its MAC table. So if PC1 goes to ping somebody in the other network, it doesn't need to ARP again because it's already got the router in its MAC. However, if PC1 were to ping PC6, it's going to need to ARP first, right? Because it doesn't have, now I ARP first, right? Notice the response that's waiting, right? Because it had to ARP it out, right? But I get the second one succeeded. Now, oh man, prove me wrong. This is 1.2, right? No, 2.1. Ah. So I'm going to ping 2.1. Now that I've pinged 2.1, I've got 2.1 on my map table, my ARP table. So every machine in this entire network is storing MAC addresses so that it can shortcut this MAC discovery process. Switches are discovering their MAC table so they can know what port to forward it to. And PCs are storing what MAC is what IP, so it doesn't have to ARP again. Because you can see how disastrous ARP broadcast is, right? Because when you have a machine, like let's say this guy, pinging right? So when he sends an ARP out, look how destructive that ARP is. Look what happens. Everybody gets interrupted on VLAN 1, right? Notice that little green packet went everywhere. Because that is called a broadcast. Now what you don't want to have happen is this fateful thing called a broadcast storm. It's like Hurricane Sandy for networks, right? Because you just get a bunch of broadcasts going all the time, real frequently. Right? And ARP is typically the protocol that causes that problem. Let me show you, let me simulate that for you. I'll show you a disastrous problem. I've created a loop. Now the switches are pretty smart though. The switches will detect that loop and not let it happen. So I think that's probably what the switches did. So I may have to fool switch. Yeah, it doesn't want me to do that. Okay. All right, let's see what happens. Here goes my ARP, right? Oh, goes back out. See what happened? The hub forwarded out all ports. Oh, but the switch killed it. Damn it. Hold on, I gotta stop this switch from killing us. It may not let me kill it, but there's gotta be a way. No, it won't let me kill it. It's too damn smart. the interfaces and see, it won't let me do it. Damn it. There it goes. I got it. Now, what port is this connected to? FA04. FA04. Aha! All right, now I got it. Now we're there. Now I got everything all green. All right, so I'm going to go to this guy, and I'm going to ARC-D. All right, let's see what happens when my ARC goes out this time. It's the switch, right? Switch is going to forward this as a broadcast out all ports, right? Goes out to all ports, right? The hub is going to send it back out all of its ports, right? It's the switch. The switch has got a broadcast. Oh, look what we have here. It collided. There's a collision. Oh no! Oh, the hub won't stop. So now we have arcs going everywhere, right? Arcs are just going nuts. Arcs are going everywhere. Arcs everywhere. Everywhere arcs. And they're never going to stop. They're going to keep going and going and going and going. And they're going to keep looping and looping. So now, but right now, you know, the switch is going to handle this kind of load. But what happens if we bring up and we go, okay, right? We got more traffic going on, right? Or he tries to ping, oh, no. Right? This is where we start getting into this complexity of, you know, everybody's trying to ping everybody, right? And so this guy's going to keep at, and so he's just going to get worse and worse, right? So anyway, that gives you an idea. So arcs will just go crazy, and they could eventually just slaughter your network, right? And so that's called an arc broadcast storm. So that, but obviously switches are designed to not let that kind of thing happen, right? But you know, you got to kind of understand it. So do you understand that my goal tonight was for you to understand what a broadcast domain is and what a collision domain is. That was my goal. So hopefully you understand that. You understand the conceptual difference between switch and a hub. So there you go. All right, any questions? All right, how many of you have done the activity in Blackboard, have done these three activities? So I can guarantee you that you're going to have some problems with activity 7.6.1. It's a little complex. So this one is going to require you to meld the knowledge from previous variable length subnet masking and some of this new stuff we're talking about. So you have to merge those together. So I would recommend that during this next week, you try to challenge yourself to try to figure that one out. And we will go over that one in class together, just to make sure you got it next week. It's hard, and this one's going to be hard. Now I've taught you in this class everything you need to know to do that. So you've learned, as of tonight, everything you need to know to complete that entire assignment. Now, I don't know if that necessarily means you'll be able to put it all together to figure it out, but I want you to try. And then next week we'll go through it together as a group, and I'll help you figure it out. We're getting down to almost Thanksgiving, which means that you're getting to about a month left to finish all Cisco assessments. So if you haven't started on that process, I highly recommend that you do so. All right, we're good. I'll see you next week. Oh yeah, do not leave your computers in the current state, right? I want them back on the internet, blue cables plugged back in, logged back on as a student account to test them. So do that. I've given you plenty of time to get that done. Yeah, put the cables back in the box, please.